We're talking about the chain rule, and we're finding the derivatives using the chain rule. So we're supposed to find the derivative, and we're probably going to have to use the chain rule somewhere in this problem, but keep in mind that we have learned some other rules too, so those can be incorporated as well. So our first function is h of x is equal to sine of cosine x over 3. So we should be looking at how to do this with a big picture. And notice that we do have a quotient, but it's divided by 3. So the preferred way to do this problem actually is to treat this as 1/3 times sine of cosine x. Then we can use the constant multiple rule for the times 1/3, and then we just have to handle the sine of cosine x. So a quick note before we get going with that is to note that what we have here with sine of cosine x is not the same thing as cosine x sine x. They mean different things. Oops. Obviously those are different things. Not sine x, excuse me, cosine x, written in that order. So it makes a big difference without this x following sine, because it means that we're taking sine of cosine x, which makes it a composite function. Alright, now that we have written our function in this form, we want to look and see what the big picture is. So the big picture here is we have the constant multiple rule, which has become something that we don't even really care about after a point because we get so used to using it. But I guess that's the biggest thing. And then also that we have sine of cosine x, which is a composite function. And the rule that has to do with derivative of composite functions is the chain rule. So now let's go ahead and take this derivative. So I'm going to indicate that with the prime notation, h prime of x, and then the constant multiple rule, we have 1/3 out front. And now we need to identify the inner and the outer function. So the sine is the outer function, and the cosine of x is the inner in this case. And we want to think of the chain rule in a simple way without a lot of notation, as the derivative of the outside evaluated the inner function times overall the derivative of the inner function. So since the derivative of the sine is cosine, I'm going to write that down, and that's the derivative of the outer function. The derivative of the outer function evaluated the inner function is just copying down what that inner function is, in this case cosine of x. And then overall we're going to multiply this. I'm going to insert some parentheses or grouping symbols that aren't really actually needed, but just to make it really clear here that it's overall and it's not embedded in that outer cosine function. We're going to multiply by the derivative of the inner function. The inner function is cosine x, and so we multiply by its derivative, which is sine x. And we're done. So let me label a few things. This is the derivative of the outer function evaluated at the inner function. And then we have our constant multiple here. And then we have our times negative sine x, which is the derivative of the inner function. So I'm just going to clean this up a bit and write it in simplified form by taking the negative and putting it out front. So we have negative 1/3 overall. Then I get to write the sine x out front so I don't have to use some extra grouping symbols. And then it's cosine of cosine x, which be really careful here. I cannot write that in simpler form. It's tempting for some people to write this as cosine squared, but that's not what it is, so you can't do that. So I'll just make a note of that. This is not cosine x times cosine x, which is equal to cosine x, that quantity squared, which shorthand is written as cosine squared. So that's it for this one. We're getting to the point where we can do problems in multiple ways, and this is not the preferred way, but it's a common thing for students to do at this stage. So I'm just going to outline here another way, and I'm going to bracket it off because it's not really necessary to do it two ways, but just to show you what a common thing that people do. And that is, they don't simplify first or notice they can use a constant multiple rule. And so they notice, however, that they have a quotient. And it's perfectly fine to use the quotient rule when you have a function of x divided by a constant. That's all right to do. It ends up being a little bit more work, but it gets the job done. So what if we just handled it this way and we found h prime of x by using the quotient rule? I'll show you what happens. So here we'd have our h prime of x being equal to g f prime minus f g prime over g squared, where the top is our f and our bottom is g. So then, starting to work on this, our g is 3, our f prime is kind of some work, it involves the chain rule. So if I don't feel like doing that off the bat, I'm just going to write down some notation that says I intend to do it. Eventually I just want to think about it a bit, and I'm trying to write out the whole quotient rule. So then we have minus f, which is just the sine of cosine x. And then that is being times g prime, which here's the critical step. The derivative of g, which is a constant 3, is 0. This is all over g squared, which is 3 squared. Okay, this is fine. Notice that the times 0 is going to eliminate the whole entire term on top. And now we have to find the derivative of sine of cosine x with the chain rule, which is something we did in the previous method. So we have our constant multiple, or we have 3, excuse me, not constant multiple. Just the 3 up front, and then we're going to take the derivative of the outer function of sine, which is cosine, evaluate the inner function, which is cosine of x, and then we're going to multiply that overall times the derivative of the inner function. Derivative of cosine is negative sine, and then we have minus 0 over 3 squared. So overall, we'll have a pair of 3's that cancel. And what do we have behind? Well, we have negative sine x out front times cosine of cosine x all over 3. Now note that this is equivalent to multiplying by negative 1/3, and then we have the rest of our result the same as by the other method. So this is fine, but notice that it was a little bit longer and more involved. And this is not the fastest way to do this. So this gets the job done, but method above was better. It's faster, it's simpler. And moving towards efficiency with taking your derivatives is something you want to do in the long run. So that's it for this one.